Welcome to Visual Engineering, where complex ideas become easy to understand through immersive visual breakdowns. If you enjoy visual explanations of AI, software engineering, and cutting-edge technology, consider subscribing, and let's begin.
Picture a single server sitting in a data center. When only a few dozen users log on to check an email or load a web page, that machine handles the trickle of requests without breaking a sweat. But if a service suddenly goes viral or a major news event breaks, that trickle becomes a tidal wave. Thousands of concurrent requests hit the network port in a matter of seconds. Every machine has strict hardware limits. When the server's CPU and RAM reach maximum utilization, it starts dropping connections. Data is lost. The system locks up, flickers, and dies. Relying on a single physical machine creates an absolute ceiling on capacity. If the hardware is overwhelmed, the entire application goes offline. The earliest attempt to fix this was vertical scaling, simply buying a larger, more expensive server with more processors and memory. Yet no single machine on Earth, regardless of its price tag, possesses the processing power to handle modern global internet traffic on its own. The alternative is horizontal scaling. Instead of building one massive supercomputer, engineers distribute the workload across a fleet of dozens, hundreds, or thousands of smaller, standard commodity servers. This creates an immediate logistical hurdle. When a massive swarm of inbound traffic arrives at the data center, the data packets have no inherent way of knowing which specific node in that vast fleet has the capacity to process them. Simply adding more hardware doesn't solve the problem. Without a mechanism to organize the inbound traffic, you end up with gridlock rather than increased capacity. This is where the load balancer comes in. It acts as an ultra-fast intermediary positioned directly between the internet and the server fleet. It intercepts every single incoming connection, evaluates the backend resources, and instantly decides which server should handle the request. The simplest logic it uses to do this is called round robin. The load balancer distributes incoming requests in a strict repeating sequence across the available servers, but round robin is blind to actual server load. If one server gets bogged down processing a heavy database query, the algorithm ignores the delay and continues to send traffic to that exact node, creating a localized bottleneck. To prevent this, engineers use dynamic algorithms like least connections. The load balancer actively tracks the number of active sessions on each machine and routes the newest request to the most idle server in the pool. By reading real-time metrics, these routing algorithms transform a rigid collection of hardware into an adaptive, self-managing system that actively avoids congestion. Many applications require session persistence. If a user is adding items to a shopping cart or securely logged into a bank, their requests must continually route to the exact same backend server where their session state lives. Traditional routing relies on simple math to divide traffic. If a single server crashes or a new one spins up, the total number of servers changes. The math recalculates, the entire distribution reshuffles, and nearly every active user is suddenly routed to the wrong server, destroying their sessions. This diagram illustrates consistent hashing, the mathematical solution used to preserve those sessions. Instead of simple division, it plots both the incoming users and the servers onto a continuous ring. If a server fails and drops off the ring, only the users attached to that specific node are reassigned, sliding clockwise to the next available server. The rest of the network remains perfectly anchored in place. It acts as an invisible mathematical tether, ensuring that a localized hardware failure doesn't trigger a massive wave of disconnected users. In a global infrastructure operating thousands of machines, hardware failure is not a possibility, it is a daily guarantee. Load balancers manage this reality using active health checks. They constantly send automated radar pings to the backend fleet, verifying that each machine is online and ready to accept data. The precise millisecond a server fails to return a health check, the load balancer strips it from the active routing pool, ensuring that client traffic never hits a dead end. To execute these checks and route data accurately, load balancers must read the incoming traffic. How deeply they inspect that traffic depends on the OSI network layers. A Layer 4 load balancer operates at the transport layer. It makes incredibly fast, blind routing decisions by looking only at the IP addresses and port numbers on the outside of a data packet without opening it. A Layer 7 load balancer operates at the application layer. It takes slightly longer because it opens the packet to inspect the actual HTTP content, allowing it to read URLs and direct something like a video request specifically to a high-capacity streaming server. Engineers weigh this exact trade-off, the raw speed of Layer 4 versus the granular intelligence of Layer 7, when designing networks to handle different categories of digital traffic. If all inbound traffic must flow through a load balancer, that device inherently becomes the network's most critical single point of failure. If it goes down, everything stops. Network architects solve this by deploying load balancers in high-availability clusters. They'll run in redundant active-active pairs, continuously syncing data so that if one unit dies, its partner immediately assumes the full traffic load. As the internet grew to serve billions, managing that traffic volume eventually outpaced the capacity of physical hardware appliances. Load balancing had to evolve into distributed software systems. This architectural diagram shows Google's maglev, a distributed software load balancer bypassing hardware constraints to achieve massive throughput. Using equal-cost multipath routing, edge routers distribute incoming traffic across specialized software nodes, which then uniformly forward packets to service endpoints. Reaching global scale requires moving traffic management into the software layer, where it can scale out horizontally to match the growing footprint of the network. These invisible systems are what allow billions of concurrent users to stream movies, to hail rides, and execute financial trades simultaneously without experiencing delays. The combination of horizontal scaling, routing algorithms, and health checks creates the modern experience of elastic, ever-present compute power. The internet remains instantaneous and resilient despite the failure-prone nature of physical hardware. Its stability depends on the load balancer's ability to silently orchestrate the chaos.
Thanks for watching. Subscribe for more visual breakdowns of AI, software engineering, and technology. See you next time.